Our third speaker is George Arnold from the National Institute of Standards and Technology.
Okay, I'm actually not going to use slides, so let's get this out of the way. It's a little bit dangerous, but I would point you to our website, nist.gov/smartgrid, where you can find a lot of interesting things. But what I'd like to do is pick up on, Eric and Henry both mentioned the smart grid. So I'd like to spend a few minutes and explain what it is and why we're doing it. I'd like to explain the way we're going about it in terms of the government role, and I'll explain what my agency's role in that is, along with the Department of Energy. And then I'll spend most of my time talking about what I believe are the major research challenges that the research community can contribute to. Well, the smart grid is, in a nutshell, the modernization of the electric grid. The system that we have today, while it's had many innovations and improvements, has a fundamental architecture that's remained the same for about 100 years. One of the reasons for that is that the regulation in the industry, for whatever reason, provides a disincentive to investment. So if you look at the R&D that the electric utility industry puts in, it's about 0.2% of their annual net revenues, whereas the overall average for industry in the U.S. is about 4%. So the dog food industry spends more on R&D than the electric utility industry. Sure. EPRI's funding from industry has been cut back dramatically over the decades. Yeah.
So deregulation killed that pool.
Right. So this is a policy issue that we'll have to get worked over time. But the basic problem is we have a very aging system, and electricity is more important than ever. We need reliable, high-quality electricity to sustain our lifestyle and our economy. So modernizing the system is an imperative. The system is very fragmented. We have about 3,200 electric utilities in the United States that own and operate the system. Most of them are in the private sector, and it represents about $1 trillion in invested assets. So the concept of the smart grid is to apply information technology and communications technology integrated into the power system to obtain some benefits that I'll describe in a second. A lot of what we're doing today uses technology that has been around for decades. And I can tell you one of my first jobs when I went to work at Bell Labs in the 1970s was the automation of the maintenance and operations of the telephone system. And a lot of what we're doing today in the electric grid is exactly what we did 30 years ago in the telephone network. There are 4 goals in doing this. One is to reduce the cost of producing and delivering electricity. A second goal is to allow the system to accommodate a much greater percentage of renewable generation and distributed generation. A third goal is to improve the reliability of the system. And a fourth goal is to enable the system to support a large fleet of electric vehicles. Well, first of all, cost. Why is cost an issue? If you look at the generation of electricity in the U.S., about half of it comes from coal, and about half of those coal plants are more than 40 years old. In the next decade or two, they're going to have to be either upgraded with cleaner technologies or replaced. And one estimate of the cost that will have to be invested in generation just to keep the lights on over the next 20 years is about $600 billion. That's going to put tremendous upward pressure on electric rates. So whatever we can do to make the system, both in terms of generation and delivery of electricity, as well as the end use, more efficient and allow us to use less electricity for our lifestyle and economy, the less we're going to have to spend to replace this aging generation. There are several ways you can make the system more efficient. I don't have time to get into that, but so cost is a major element. The second is renewables. As long as you don't have too many of them, the variability and the fact that you can't control when the wind blows or the sun shines isn't an issue. But if you start to get larger percentages of that, the system moves from being what it is today, a very deterministic system in which you can control generation. We have to deal with a much more stochastic system. And so the information management in the smart grid is, is intended to address that. Reliability. In most parts of the country, the electric utility does not know when you have a power failure at your home unless it affects a very large neighborhood. If you look at the reliability statistics, we have about 2 hours or about 130 minutes a year of outage on average per person in the US. The comparable figure in Japan is about 16 minutes a year per person. So the system can be much more reliable than it is today. And one estimate done by one of the DOE labs is that these outages cost our economy about $80 billion a year. Okay, so the fourth goal is supporting electric vehicles. Again, as long as you don't have too many of them, it's not a problem. But to fast charge an electric vehicle takes about the same amount of power as it is to run a whole household. So if you have a neighborhood where many people are going to be having electric vehicles, all of a sudden you've doubled the load on the system, and the distribution transformers are just not designed to handle that. So you need to have some intelligence so you can have some interaction to control when vehicles charge, how much they draw, and keep the system running. So that's why we're doing this modernization that we call the smart grid. Now, to do this, Congress recognized that it was unlikely to happen in a environment where you have 3,200 independent utilities. Right? There needs to be some sort of guiding force, some master plan to make this happen. And so in 2007, Congress passed what is known as the Energy Independence and Security Act. We call it EISA for short. And Section 1305 of that act lays out the national policy for the smart grid. So I'd like to point out that even though Congress has not, who knows when they will ever have an energy policy for the U.S., at least we have a smart grid policy. And we're probably the only country that actually has a law that describes it. And if you go to that act, it's very interesting because it really paints a vision that Congress has of moving away from this legacy system that's optimized to have central generation, a one-way flow of electricity out to end users in a very deterministic way, to a much more dynamic system where you have a lot of renewable energy, much of it distributed. You have appliances that are smart and can react to conditions on the grid, and so forth. That's all described in the Act. The Act also described the roles of the various government agencies. So the Department of Energy is the lead at the federal level, and has jump-started deployment of the smart grid with about $4.5 billion of Recovery Act funding, matching grants to private investments that will at least get a start on implementing the smart grid. The Act also directs my agency, NIST. We used to be called the National Bureau of Standards. Now we're the National Institute of Standards and Technology. We're part of the Department of Commerce, but we work very, very closely with our colleagues at DOE in this program. And our role is to coordinate the development of the technical standards that are needed to underpin the smart grid. It also assigns a role to the Federal Energy Regulatory Commission to adopt some of the standards coming out of the NIST work in federal regulations, and that's another interesting area for policy wonks that we could get into on a different occasion. So let me now turn to what I think are some of the important research challenges that we have ahead of us. First, I would observe that we have about 30 years of catching up to do in applying current technology to the grid. So just about any problem that you can imagine was worked in the telephone network or the internet over the last 30 years, there's probably an analog to it in the electric grid that we haven't tackled. I would say that In addition to developing new technologies for things like electric storage and some of the things that you've heard from Eric and Henry, there's also a major challenge in actually making effective use of existing technologies in these new grid applications. And while you would think that is just a mundane engineering problem, it's not, because the electric grid, unlike the telephone network or the internet, has to obey some of the laws of physics, including Kirchhoff's law. So some of the degrees of freedom that you have in these other networks, you just don't have in the electric grid, because things happen at the speed of light. So in thinking about taking some of our sort of current and emerging technologies and applying them to the grid, research in terms of how do they meet up against these constraints that did not exist in the other applications is an important research problem. So I'll identify 7 areas that I think are important topics for research. The first area is the architecture and standards for the grid. That's the area that personally I focus most of my energy on. This is important because if you talk to someone like Vince Cerf, who's designed IP protocol, he'll tell you all about the things that they would have done differently if they had envisioned how the internet might be used someday. So a lot of the sort of security issues that we have in the internet today really stem from very sort of basic design decisions that were made 30 or 40 years ago. So getting this right for the electric grid is very important. A second area of research is the application of communications, data communications, for control system and sensor networks in the grid. And you would think that, well, why is this a research issue? Because it's just a matter of applying all the tech. We've got a rich set of technologies. We just apply them to the grid. It's not that simple, because you have to look at some of the latency requirements, for example, in operating control systems for the grid, where the latency requirements typically may be in milliseconds. And unlike let's say the internet, where if you have a little bit of delay, you just get, buffering takes care of it, and you probably wouldn't even notice it. The consequence in the electric grid is a generator could be destroyed, or there could be a cascading failure as a result of not closing a relay soon enough. So understanding the performance requirements for different communications applications, and whether existing communication technologies and protocols can be used as is, or whether they need enhancement, is an important area. A second area is data management. And just to give you a few parameters here, the U.S. Library of Congress collection represents about 200 terabytes of data. All of the videos on YouTube represent about 500 terabytes. If you think about when we get around to deploying smart meters in every home in the U.S. and the sort of 5-minute interval data they'll be collecting, that will represent nationwide about 60 petabytes of data a year, or 60,000 terabytes of data per year. That's a lot of data. But it's not that we can't handle it, because Google processes about 4,000 petabytes per year. And so the smart grid is probably not going to stress us beyond our capabilities, but understanding how to do this in a very distributed system is going to be important. Third area of research is the dynamic sort of modeling and control of a much more dynamic system. The introduction of renewable energy, storage, smart appliances that will react to dynamic pricing. This is going to work very differently than the deterministic system that we have today, and so we need new models to characterize and understand how to control these systems. Forecasting models. Forecasting has been very, very important to the electric utility industry for decades, and forecasts of demand are very sophisticated and work very well. The trouble is that everything's changing. We're going to have appliances that will be making decisions on their own about when to run and how much power based on the price of electricity. Electric vehicles will be roaming around. Won't quite know when and where people will want to charge them. We're going to need forecasting models that take all this into account. Sixth area of research is sensor networks and data integration. In addition to the smart meters, one can imagine sensors in the network that will identify when transformers are about ready to fail. There's going to be a lot of data that is collected. How to manage that, how to make use of it is going to be critical. And the seventh area, and perhaps the most important, is cybersecurity. The introduction of these new systems. Well, actually, the smart grid is an opportunity to improve the security of the grid, because a lot of the control systems that we have today have been around for a long time before good computer security practices were in place. But threats are going to be constantly evolving, and these systems will have to be highly secure. So research into the evolving nature of the threats to the grid and how to mitigate against them is going to be an ongoing challenge. So those are just a few thoughts on some important research topics for the grid as we move forward, and I'd like to thank you for your attention.